So when people think about NASA, what do they think about? Well, they typically think about space exploration. This is a really cool example of one of these 3D assets I found just by typing Apollo. So this is a point cloud. It's a point cloud that was generated from the actual photographs the astronauts took, and by combining multiple photographs, you can get a 3D image, sort of. I mean, you can't get behind it too well, but you can see the astronaut, you can see the lander, you can see the flag, you can see the rover. Apollo 17 was the last time we sent people to the moon. That was in 1972. So what is that? That's now 52 years ago. And we haven't been back yet, but we're on our way back with Artemis. I also did a lot of driving, so they used that rover more than any other mission. So maybe that's what you think of when you think of NASA, even though it's 50 years ago. We're still exploring the moon, but we also do science. And maybe what you think about are images like this from the James Webb Space Telescope. Um, I mean, JWST has been wowing us with all kinds of gorgeous images. This one is a young star, baby star. It's a kind of star. It's called a Herbig-Haro object after the discoverers, or HH. But what's going on here is that stars form out of dust and gas. And as they start pulling that in that early phase, they're still sucking in a lot of material. And as part of that, as it spins up, as more material falls on, they'll often, for a brief period of time, launch these jets. And here you're seeing these two jets being launched out from the center. We actually can't see the star because it's shrouded in the really dense gas and dust that's falling on to make that star at this moment. But you can see really cool structures as material is shot out by magnetic fields, and it smashes into other things and glows in all kinds of beautiful colors. So this is also, I mean, Jonathan mentioned I'm an astronomer, but also not what I'm going to talk to you about today. What people are less aware that NASA does and has done for all of its history is study the Earth. And where I work at the Goddard Space Flight Center, there are more working research Earth scientists than any other institution in the world. 1,300 Earth scientists. All right, so let's look at some of that work. Here's one of the visualizations that my group does. We produce this video every day to show you what the orbits will look like the next day. And we update an image every 10 minutes on our website. And what you're seeing is NASA's Earth observing fleet. So this is the full set of satellites that is observing the Earth right now, NASA satellites. We also have other satellites that we built but are operated by NOAA, one of our partner agencies. And so you can see, you can read some of the names there. We're gonna explore a couple of these. You might notice going around the left side, around the bottom now, Landsat 9. That's the latest in a series of satellites that have been going for 50 years. PACE up at the top is our newest mission, and we're really excited. Pay attention around Earth Day. We're going to be releasing the first images from that. It just launched a month ago. And then maybe you just saw crossing up the ISS, the International Space Station. That's also a platform for science as well. So let's take a look at one of those missions. This is the Landsat satellite that I mentioned. Again, I just got this by typing in Landsat, and I had lots of models to choose from. This is the Landsat 8. We're now up to Landsat 9, and they all look kind of the same. And the thing that makes this special is the fact that we've had this continuous set of observations. We've replaced one satellite with the next. And what that does, it allows us to observe change of our planet over time. Let me give you an example of what some of those images look like. This is an image, a high resolution mosaic image taken by that spacecraft, by Landsat 8. And this is of the area I live in. This is the Chesapeake Bay region. So here's the Chesapeake Bay. We can see some of the major urban areas. This is Washington, D.C. I zoom in, I can see the National Mall. I'm going to actually show you a picture of this tidal basin a little bit later, so keep this in mind. I'm going to show you a tree that lives right there, a tree called Stumpy. This is the Jefferson Memorial. We also see another city, Baltimore up there. And over here is the city I live in, Annapolis, Maryland, and we live down here somewhere. But what you get by observing over time is you can see cities grow, you can see forests being cut down in the Amazon, you can see the color of the oceans change, and the color of the oceans tells you about what's living in the ocean. Yeah, I just love this image. So yeah, if you want to explore this is a zoomable high resolution image. Just scan that QR code and you can zoom it on your phone. Now, I mentioned how nice it was to find some things. Here's some examples of people taking Landsat images and adding that with terrain and building 3D models that you can, again, find just by searching in the search bar in Snorkel. And this height information actually came from an earlier NASA mission that was aboard the space shuttle. So this is the image of a glacier in Greenland, and this is an example of the kind of thing we want to track over time, because we know that the glaciers are retreating. We know that the ice is melting off of Greenland, and actually that the loss of mass and ice from Greenland is causing our seas to rise globally. So tracking this over time is very important. It's also beautiful. All right. Any guesses as to what this is? I'll give you a hint. People climb up it, some people. And I was just looking to see which is the way people climb. Well, let's see, we got an answer in there. Yes, it is indeed Mount Everest. And the most common route is the southern route, which comes up the back here and up this ridge. But the second most common is up this north ridge, this route right up there at the top. Anyway, there's some amazing collections of Landsat imagery. There's a whole collection they call Earth is Art because it's just abstract, beautiful imagery. There are also things like this. So this is a giant volcano in Chile, but the terrain, I love this because the terrain to me looks just like the terrain of Mars. In fact, Mars has giant volcanoes, giant shield volcanoes, very much like this. And so to me, it's like we're looking at Mars. And in fact, there are missions that go out that use the deserts in Chile as Mars analogs to practice driving the rover, or say, practice the kinds of just even living in a harsh environment at high altitude. All right, yeah. So encourage you to explore these yourself. And so that was a little about Landsat. I mentioned that one of those satellites I showed was the International Space Station. So here you see the space station. And space station is not just, it's not just a place that people go. It is a platform for science. And we have a bunch of science missions on there. I'm going to just talk about two of them. So if I zoom in here, this whole area that I'm circling here is it's the, the the Japanese experiment module is the name of this. And on this module, you see here, each of these little boxes is a different experiment. We're going to talk about this guy here. This is an experiment called Jedi, like in Star Wars, although it's Jedi with a G, not Jedi with a J. But yeah, exactly, like Olympus Mons, Liam. Jedi with a G, but the scientists working it have leaned into the Jedi, the Star Wars analogy. One thing that strengthens that is not just the name that makes it like Star Wars, it also has its own sort of lightsabers. So it's constantly sending a beam of lasers down to the Earth and looking at the light that's reflected back. So this is called LiDAR. And what it's doing is it's measuring the height of forest. And actually, not just the height of forest, but it's actually giving us a three-dimensional profile of the trees. So we can see where they're really tall trees, where the trees are healthy. We can actually see, where it's old growth forest or maybe newer forest. And we can actually, in some cases, begin to discern by this pattern, this three-dimensional pattern you're seeing, the different types of trees in different areas. So let's take a look at what that looks like. Here's this map of the eastern United States, and it's centered right on right where the Goddard Space Flight Center is, where I work. And you'll see, because it's aboard the ISS, every time the ISS passes over, it measures the tree height along a little line. But as a year goes past and the ISS passes overhead every 90 minutes, you can build up a more or less complete picture of tree height across the globe. Let's watch that again. You kind of notice it'll go up once and down once and forms this sort of crisscross pattern. And if I zoom out, I'll take a global view of that. And that's what you see here. So this is actually a visualization I'm very fond of. We kind of call it the moss earth because it kind of feels like you could almost touch it, right? You'll also notice that we don't have measurements, tree height measurements in the Arctic. And actually, it's harder to see, but that's also true in the Antarctic. Does anyone know why? Any guesses why?
It's okay to call out.
Yeah, exactly. It's the satellite path, and it's the orbital inclination of the ISS. If we went back to that other video, see it's coming up and down this angle, and it never gets over the poles. So this is a great technique for collecting data, but we can't collect data on the poles. We have other satellites that do that. In fact, there's one called IceSat, which does a very similar thing, but it's more targeted at ice. Even though it's called IceSat, it actually does measure the height of trees as well, though. All right, let's go back to the ISS. And I'm going to zoom in. All right, so there's also some experiments over here. This little platform here is called ELC1, Express Logistics Carrier. And in this slot, there's an experiment which hasn't made it into the model yet, but it's an experiment called EMIT. And EMIT is pretty interesting. EMIT was designed to look at minerals, different minerals on the Earth. It just came out with its first mineral map, so it's able to detect 10 different kinds of minerals. It's hard to make a map of 10 different kinds. So here are 3 of the more important kinds. It's a very colorful map, but to be able to see those minerals, it needs to be able to see the ground. So it's only really able to observe in very dry places. So the Sahara, Northern Africa, the Western US where it's drier, Australia. But say over the Eastern US where you're looking at trees, it's not able to make these measurements. You can kind of zoom in on this beautiful map. In detail, like you have to be a geologist to care about these differences, but the reason why you want to know about them is that these are minerals that have important effects on our atmosphere. They get blown up, dust storms over the Sahara in particular, and that can have implications for cloud formation, precipitation, even our climate overall. So that's what this experiment was designed to do. But one of the cool things about EMIT, and the reason I wanted to talk about, is that sometimes when you build a satellite or you build an instrument for a satellite that's designed to measure one thing, once it goes up there, people find out actually it can do more than people thought. And yeah, most of the sensors are, it's mostly in the infrared is what it's detecting. That's right. And one of the unexpected discoveries of EMIT is that it's able to detect methane, the gas methane. And methane is a very important gas because it's a greenhouse gas. It's one of the gases that's causing our planet to warm. In fact, it's an extremely strong greenhouse gas. It's about 80 times stronger than carbon dioxide. EMIT can't detect all the methane, but it detects very strong emissions of methane. And that's actually important because it turns out that sometimes industrial activity, sometimes natural gas or oil extraction can leak methane, which is a really bad thing. Sometimes they don't know. We can now detect it from space. And this is an example over Jordan. Although people are very sensitive about like who gets labeled, so maybe I should take the label off. Of one of the early examples of methane plumes being actually detected several times from this one location. You see it going around in different directions depending on which way the wind is blowing. The good news is that by having satellites up there that can detect these leaks, we can identify them and hopefully stop them. So that's really the next step, is feeding back this information. Actually just another satellite was launched that designed to do this and help us track these methane leaks globally. And it can have, I think, an important effect on our planet. So speaking about greenhouse gases and global warming, I just wanted to point out one of the other things NASA does is not just observe, but we also run computer models taking those observations to better understand how our planet works. This is a model that was run at the National Center for Climate Simulation, which is right next to my office. That's why my office is very cold, because they keep cooling the supercomputer. And what you're seeing is actually something that has not been released to the public yet. So I'm giving you a sneak preview. You guys are one of the first people to see this. This is the highest resolution model of global carbon dioxide that's ever been made. The pulsing you're seeing is the breathing of our planet. You're seeing trees during the night, they breathe out carbon dioxide. And during the day, when they're photosynthesizing, they breathe it in. And every pulse is a daily cycle. You're also seeing emission of carbon dioxide from industrial centers. Now we see it, for example, over China. And by able to track this, so we're just getting a better understanding of how carbon dioxide flows across our globe. And of course, carbon dioxide I mentioned that methane was much more powerful, but carbon dioxide is the main driver of climate change, because there's far more of it, and also because it lasts much longer in the atmosphere. And speaking of climate change, another thing that NASA does is it keeps a record of global temperatures, and it does this by taking all the temperature measurements that were made both by weather stations on land or by buoys and ships on the sea, and combines that together to measure a global temperature. And what you're seeing here is a map of that temperature over the last 140 years. The blue spots are spots that are colder than the average temperature. The red spots are spots that are hotter than the average temperature. And what you probably saw early on was there's a mix of blue and red spots. But now when we get to last year, 2023, it's almost all red. In fact, it's very red. And 2023 was by far the warmest year on record. We're seeing some, another way we measure climate change is through the height of the ocean. So one of the things that NASA's been able from satellites for the last 30 years, we've been able to keep a very accurate measurement of the average global sea level temperature, and it creates this graph. So what we've seen is a rise of about 10 centimeters, about 4 inches over 30 years. If we go back, that's the satellite record. If we go back to earlier records, the last 100 years, we've seen about a 1 foot rise. What does that mean? Well, I think both we got an example last weekend. Well, let me first say, like, here in Washington, D.C. area, it's a beautiful time. The cherry blossoms just hit peak bloom yesterday. And anyway, viewing the cherry blossoms is a big sport here in this area. Last Saturday, we went down, as I mentioned earlier, to view them. This particular tree is a very famous tree. He's obviously not in very great shape. His name's Stumpy. He has his own Facebook page. And Stumpy is telling a lesson about how our planet is changing. This year, the cherry blossoms have bloomed far earlier than any other year, and that's because of how warm it's been. And also, if you look carefully, you see that the water is around Stumpy's base, and that's part of the reason why Stumpy doesn't look so good. Stumpy's regularly getting flooded. Turns out it's mostly not the seas rising. There's a sea wall that protects that keeps the sea out, and that has been sinking. So that's sunk 1 foot over the last 100 years since this tidal basin was built at our nation's capital, and the seas have risen 1 foot. So you get 5 feet down and 1 foot up, and the result is that twice a day, poor Stumpy gets flooded, and Stumpy's not doing too well. They're going to fix that this summer by putting in a new seawall, but unfortunately, Stumpy is going to have to be removed. So this is Stumpy's last cherry blossom season. All of which is kind of sad, but I want to leave you with some hope. And also invite you, if you're ever in Washington, D.C., to come see the big display we have there. This is called the Earth Information Center. It's at NASA headquarters in downtown D.C., not too far away from the National Mall if you're visiting the Smithsonian. And Why do I have hope about climate change? I have hope because many people are working very hard on solving the problem. And we've created this, what we call the Earth Information Center, as a way to put together that information to help communities respond and adapt to our changing planet. This is a picture I took when we had a group of indigenous leaders from the Amazon come in, and they're sort of on the front lines of dealing with climate change and helping to protect the forest of the Amazon. And they've been working with NASA scientists. So there are projects like this happening all across the globe. So yes, climate change is a serious problem, but you shouldn't feel hopeless. There's a lot we can do about it, and there are a lot of people are doing about it right now. All right, I'll stop it there, and happy to take any questions.
Awesome. Thank you so much, Dr. SubbaRao. Let's give our speaker a virtual round of applause. That was great. That was great. Thank you so much. Well, one of the challenges that I'm sure you have discovered as being a scientist, particularly an astrophysicist, is that you'll get questions that can span any corner of science. So, yeah, we'll open it up to some questions. I know that in the chat we already had a question of what were the sensors for the methane and CO2, and can they be detected via IR?
Yeah, so in both cases, you're looking at an infrared spectrum to try to piece it out. Carbon dioxide in particular is a very difficult molecule to detect from space, because probably when you're looking, you have a mix of all these different things, and also you want to be able to look through. So what I showed you was not like observations, that was a model. I could show you the observations, but it just doesn't look nearly as pretty as the models. And what we do is we take those sort of top of the atmosphere models, we combine them with ground stations, for example, that NOAA runs around the globe. When we combine that with our information about where the cities are, we actually look at the night lights to get an idea of where people are emitting carbon dioxide, and sort of combine that all into these very complicated models that I showed you in that visualization. But yes, there are a couple. There's for example, there's an instrument. It's called the Orbiting Carbon Observatory that uh, makes these maps of carbon dioxide, and we have some new ones. Satellites hopefully will go up in the near future.
There's a question about methane, whether it is mainly from the cow industry.
No. Well, mainly no. There, I have another visualization about that. If you want to go to sbs.gsfc.nasa.gov, you can search and get a map. But agriculture is the leading sort of grouping um, is the most of the methane comes from agriculture. It also comes from natural sources like wetlands. It comes from oil and gas extraction. There's like leaking of natural gas pipelines, and it also comes from our landfills. Landfills are actually is probably one of the easiest places to stop methane emission. There's been a lot of attention to methane lately because it has a big effect, and it's something that we, with enough effort, we can really tamp down our methane emissions. Termites are also a source of methane. So, cows are a source, but I think everybody just thinks methane and cows, and you could take cows out of the mix, and it wouldn't make a huge difference. An important difference, but not a huge one.
Awesome. A question was, how much will the sea level rise if it keeps rising at this rate?
Yeah, and one of the interesting things is how much really depends on us. At least the numbers I've seen. So our biggest uncertainty is how we're going to respond. to climate change and how we're going to change our behaviors. We've already seen, if we went back like, say 5 years ago, like some of the worst projections are not going to happen. And they're not going to happen because we know we're behaving better than we had been. And we're starting to see, for example, in the United States, emissions went down last year by a pretty significant amount. And the difference in those different scenarios for how we how strong our emissions are in the future make a big difference. So it's a difference between sea levels rising by a couple feet, and we think they've already risen by a foot, or rising 6 feet, in the worst case, maybe even 10 feet by, say, the year 2100, which is still ways off.
Well, that's terrifying. So just
Yes, I'm going to root for 1 foot. Let's aim for 1 foot. They're going to still go up, but like I said, that's in a worst case scenario, and I think we are. I don't expect that we'll be in the worst case scenario.
We have a follow-up question on the methane. Doesn't methane trap heat, helping the greenhouse effect? Is that what methane
Yes.
kind of does?
Yep, that's exactly what it does. That's correct.
So I actually had one question. Algae blooms are obviously a huge issue for many communities
Yep.
near the ocean. Can some of the space missions, observing the Earth, help to predict blooms?
Yeah, and that's this mission I mentioned that just launched last month called PACE, and it really has 2 parts to it. Um, it's I'm gonna have to remember what PACE stands for, but it studies the aerosols and things in the atmosphere, but it also studies the color of the ocean. And this is where we really track. We can actually not just track um, algal blooms and measure them. We think we can actually model different populations, and it's I just the lead, Jeremy Wardell, of that project. I just was listening to him this morning, and he was explaining it's essentially this is a satellite designed to see like microscopic invisible things, and we're putting it up in space, which is kind of crazy, right? But by very carefully measuring the color of the oceans, we think we can break it down to like all the little creatures that are living in there and model their populations, and hopefully, yes, predict algal blooms, which have a huge economic impact.
Wow, that that's great. Are there any other last questions? Well, Dr. SubbaRao, you've been very generous with your time and information, so one more round of applause virtually for you. Thank you so much for joining us and for touring us through these amazing visuals. And thank you all for tuning in. We will be sharing this recording together with an interactive version of it that has these interactive visuals, so you'll be able to have this experience when you leave. And also people who missed it can have this as well. But nothing compares to being live with you, Dr. SubbaRao. So, well, thank you all and have a great night.
Yeah, thanks for coming.
Sure.